So here is our specific notation that we're going to use for the limit. We say that the limit as x approaches c of f of x is equal to some limit L, and we read this, the limit as x approaches c of the function f of x is that value L. And when we did it numerically before, we found the function f of x was equal to x squared minus 4 over x minus 2. In fact, this is the kind of function that we could reduce, and we could graph it this way. If you recall, when we were talking about rational functions back in the section 2.6, we said if we had x squared minus 4 divided by x minus 2, we could simplify that function by factoring in the numerator and then canceling our common factors as long as we accounted for the change in the domain. So we had x minus 2 times x plus 2 here, and we're dividing that by the quantity x minus 2. We note that's a common factor, and so this function f of x is exactly the same as the function x plus 2, provided that x is not equal to 2. And we said that at x equals 2, we get this hole in the graph. Okay, so what happens at this hole in the graph? Well, remember, if we say the limit as x approaches 2 graphically, we're interested in what happens to the behavior of the function as x approaches 2. So as we approach 2 from the left, it looks like the y value comes up from beneath and approaches 4. Right? We can just pick a value over here for x and see that the value for y is pretty close to 4. And if we got a little bit closer to x equals 2, we'd see that y was a little bit closer to 4, and so on. And as we let x approach 2 from the right, same idea, except at this time we're choosing values of x that come to close to y equals 4. As x gets close to 3, y approaches 4 from above. So it looks like our y values are approaching each other at y equals 4. That's what we said it should be right here. This was wrong, right? At that limit as 4. So we're saying that the limit as x approaches 2 of x squared minus 4 over x minus 2 is equal to 4, at least based on the evidence of our numbers in our graph. And this does illustrate this very important point to us. And that point is as follows. The value of the limit of a function as x approaches c does not depend on the value of or even the existence of the function at x equals c. So as you saw in our previous example, we let x approach 4 from the left and the right, and we got y equal to 3. Yes, the function y equals 3 at x equals 4 when we substitute it in, but that is a different case than what happens here, where y is not defined at all at x equals 2, and yet the function behaves as though it's approaching 4 as x approaches 2. The value of the limit, that is the behavior of the function, does not depend on the value of the function at x equals c. So we need to make sure that we are keeping these two items separate.